programming computers for about 80 years now, and yet, surprisingly, there's still not much agreement on software design or what good programs look like. And in fact, to my view, we don't even really have very much discussion of that in the field. And that's been a source of frustration to me. So in this talk, I'm going to talk about some things I've been doing over the last decade or so to try and increase design awareness in the software community. So let's start with, there've been a couple of things that have been bugging me for a very long time and that really led to what I'm going to talk about during the talk. First one is a question, and actually it's a question for you all. Question is, what is the most important concept in all of computer science? Now, if you had to pick one idea that threads its way through every major part of computer science, software, hardware, theory, artificial intelligence, machine learning, HCI, you had to pick that. What is the single most important thing? And you can just try chatting that. I'm going to see if I can open my chat window here so I can see. Just try chatting your suggestions for that. What's the most important concept in all of computer science? Indirection, modularity, I see logic, abstraction, great end user experience and value, problem solving, algorithm, lots of great ideas here. Object programming, learning, design, simplification, consistent behavior. Great, so lots of ideas here. Actually, I tried asking this question to Don Knuth, whom many people view as sort of the father of computer science. And so you might assume that if Don gives an answer to a question, it is by definition right. What Don said was layers of abstraction. So what I would say is something close to that, but a little bit different. To me, the most important concept in all of computer science is problem decomposition. How do you take a big problem and chop it up into pieces that you can solve, ideally, relatively independently? And this idea threads its way through all of computer science. So layers of abstraction is one way of, for example, of doing problem decomposition. Well, the sad thing is we don't teach this. As far as I know, except for the course I'm going to tell you about in about 10 minutes, there is no computer science class anywhere in the world where one of the fundamental, most important concepts that's taught in the class is the notion of problem decomposition. You know, we teach programming and class-oriented design, and we teach software engineering and tools, but this idea about sort of artistic, creative process about how you decompose problems, we by and large don't teach. Second thing that's been bugging me, it's well known that the best programmers are way more productive than average programmers. You know, Google coined the term 10x programmers. There was an experiment, just a thought experiment done at Google a few years ago where VPs were asked, if you had a choice, either I take away your very best programmer or I take away your N worst programmers, how large would N have to be before you would sacrifice your best programmer? And the answers were typically the hundreds, 300, 400, 500. Again, the value of these great programs are so much better than average. And yet, as far as I know, we don't do anything particular to teach the skills that will make people into these elite programmers. So these two things just seemed crazy to me. How can there be things that are so important in our field and we make no attempt to teach them in our classes? So I noodled about this for many years. And my first question was, well, is it even possible? You know, is being a great programmer some sort of innate gift that either you have it or you don't? Actually, I did a poll among the faculty, and a surprising number of faculty at Stanford thought it was a gift, couldn't be taught. But then a while ago, I read a really great book, which I strongly recommend to you, really great summer reading or airplane reading. The book is called Talent is Overrated, and it's written by Jeff Colvin. And what he does is he addresses this myth of the gifted person and shows experiment after experiment after experiment in all sorts of different areas that show if you compare the really best people in a field to just average people, what is it that distinguishes them? Is it some sort of innate gift? And the answer is no, it's not. In fact, the thing that distinguishes them is careful practice, just a lot of practice. And he shows this to be true in field after field after field. Now, of course, if you're only 5 feet 6 inches tall, you're probably not going to have a career in the NBA. So there are some limitations to this. But nonetheless, in the intellectual fields, pretty much everything can be taught and learned. So after reading the book, I thought, well, if this is true, then it's got to be possible to teach great programming skills. So the next question is, who's going to do it? So the problem is that pretty much no faculty in American universities have the qualifications to do this because they by and large don't program. Most faculty programmed when they were graduate students, didn't really have anybody to train them, didn't receive any instructions, didn't really, there was no way they could learn to be great programmers, so they didn't. And then they became faculty and they decided programming is what graduate students do. And so they stopped programming. And so as a result, faculty by and large have not developed the skills or the understanding to be able to teach great programming. Sort of ironic that every generation of graduate students tends to make fun of their professors, talking about what bad programmers they are, and then they become a bad programmer themselves when they become faculty. But there's one difference, which is that I'm actually not like most faculty. I love the program. Programming is one of the things I live for in life. It's one of my top 3 or 4 favorite things. And so I've continued to do it. If I don't write 5 or 10,000 lines of code a year, I don't feel like I've had a really great year. And over the course of my career, I've been fascinated by the idea of software design. And so even though there was nobody to teach me, I never had code reviews when I was a graduate student, I've been observing and watching code, both code written by myself and code written by others for a long time. So at this point, I probably am in as good a position to try and teach this as anybody. By the way, I should mention that even great programmers in industry aren't necessarily good teachers of this. As I was starting this whole process of creating a class a few years ago, I was fortunate enough to wangle a lunch at Google with 3 of the people that I think are among the best programmers in the world. Jeff Dean, he's one of Google's top engineers, Ken Thompson, the original author of Unix, and Rob Pike. And so I sat down at lunch with them to try and pick their minds about what are the key elements of great software design and what are the things we should be teaching programmers. And what was interesting about the discussion is that they all struggled to articulate how it was that they write great code. I still believe they're all great programmers, but it was not a process that they had considered consciously, and so it was hard for them to tell me what should I be teaching, what should I be doing. So anyhow, that just reinforces. Unfortunately, there aren't many people who have the combination of knowledge and teaching ability to teach this. But I figured I had a pretty good chance. So finally, I decided, okay, I'm just going to go for it, give this a try, and let's see what happens. So then the next question is, well, how do you teach this kind of stuff? And the formula I settled on is one that's become a new Stanford course, CS 190, Software Design Studio. And the basic idea is to teach programming kind of the way I learned English writing in high school. I assume this is still done today, which is an iterative approach. In your high school writing class, what happens is you write something, your teacher covers it in red ink, you read over the comments, you revise, you resubmit, and you iterate over this process several times. And it's the combination of first getting feedback and second, going through and rewriting so you can see the benefits of feedback. That's how you learn how to do it. And ironically, by the way, this is what's missing in most of our computer science classes. Many classes students get no feedback at all on their code quality. They get graded based on whether it works or not. But even if they do get feedback, typically they don't have a chance to go back and revise and incorporate the feedback. You just go on to the next project. So anyhow, for this class, it's designed iteratively. And the way it works is in 3 stages over the course of a quarter. Over the first few weeks, I give people a system to design and build from scratch. I give them no clues about how to structure it. They have to start from scratch. And it's not a big system, but it's the largest thing people can do in order 2 or 3 weeks, which tends to be around 2 to 3,000 lines of code. Students work together in teams of 2. Then they turn this in, and then we go through a round of code reviews where the students read each other's code, The students present aspects of their code in class and get feedback from other students in the class. And I read every line of every project and do very intensive code reviews and also meet individually with the teams. So then based on that, then they go back and they revise their projects in the second phase of the class. And actually they also add some more features at the same time they're revising. Then we do another round of code reviews on that. And then finally, in the third phase of the class, students start another brand new system from scratch, and we do code reviews of that at the very end of the class. So there's time for 3 of these iterations, and that's really tight. The class would be better in a semester format where there would be time for a 4th or maybe possibly even a 5th revision, but that's the best we can do in the quarter system. And I should say this is an extremely intensive thing for me as instructor because during each of these code reviews, I have 1 week to read 20 to 30,000 lines of student code. And that limits the size of the class. That's why it turns out I can handle 9 teams. 10 teams, I'm borderline insane by the end of the quarter, but 9 teams I can actually handle and get through the quarter without losing my sanity. So that's how the class works. Any questions so far before I start going into the material of the class? Okay, let me go on. So now you're probably wondering, what are these magical secrets to being a great programmer and doing great software design? So first of all, I have to say, I don't claim to have all of the answers. You know, that again, over the years, I've developed some theories for my own programming, but, and that's what I teach in the class, and that's what's written in the book, but uh, I'm not yet prepared to say that these are absolute fundamental truths that apply to everybody. Second thing is, I don't have a formula I can give you. I can't give you a recipe, 10 simple steps to becoming a great programmer. Nothing concrete like that. In fact, the things that I teach in the class are almost more like philosophy than concrete pieces of software design. Things like classes should be deep or define errors out of existence. These are pretty vague notions. And I realize that these probably are hard for students to integrate and use when they first start off. But I do introduce these notions at the very beginning of the class. The way they work best is in conjunction with code reviews. So once students have written code and I review their code, I can show how there are problems with the code and how those problems relate to these concepts and how you can apply the concepts in order to make the problems go away. And that's where I think it starts to make sense for students. I think, again, the concepts are kind of hard to understand a priori. So I'm going to go over 4 of these, the ones in red, in the rest of the talk after this slide. Second thing that I find to be helpful is red flags. So I've tried to develop a collection of red flags. These are things that are very concrete and objective, things you can observe about your code that tells you there is probably a design problem, that you should be reconsidering your design in order to fix this. And I think red flags are really useful for beginners because even if you don't know how to design code that's good in the first place, even as a beginner, you can recognize the red flags. And so if you just look for red flags, fix all the problems that were found by those red flags, and just keep iterating until there are no more red flags, you'll probably have a pretty reasonable piece of code. So red flags are great for getting started. I see in the chat windows a question about why not form teams of 3 to 4 instead of 2. It's a trade-off. My concern is that when you get teams of 3 to 4, it's really easy for 1 or even 2 people to not actually contribute much. That a small number of people end up doing all the work and therefore getting all the learning. Whereas with teams of 2 and reasonably large projects, each person must fundamentally be fully engaged. So I think it's better educationally, although it limits, of course, the scale of the class. So I can only handle 9 teams of 2. Another question, do you use static code analyzers to supplement code reviews? I don't typically. I get code analyzers will find these are sort of mechanical things. It's fine to use. I think those are great software engineering tools, but they don't really tell you about design issues. They're more about much more concrete things like memory leaks or bugs or things like that. Okay, so now let's look at some of the pieces of philosophy. And I want to start with classes should be deep, maybe the single most important concept of them all. What does that mean? So one way to think about this is to imagine imagine a class as a rectangle where the area of the rectangle represents the useful functionality it provides, whatever features it provides. And then the top edge of the class, which I've shown in green here, this is the interface. So that's everything that a user needs to know in order to use the class. And that's of course, it's obvious things like the function signatures and method signatures, but often it's quite a bit more than just the basic signatures as part of the interface. Every piece of knowledge that you have to have in your mind to use that class. So if you think about these two things, the functionality of the class is its benefit. That's what it's doing for you. So that's goodness. Interface is cost. That's something people have to learn. It's overhead. And so bigger interfaces are worse. More functionality is better, but small interfaces are better. So you can think of classes as being either shallow or deep. A shallow class is one that has a really large interface, but not a whole lot of functionality underneath that. This is not a great class. And the reason is that one of the key things we want to do with classes is we're trying to get leverage against complexity. Trying to find a way to have really simple ways of doing things that are really complicated. We want people to have to learn almost nothing and yet be able to do a whole lot of stuff really easily. Well, if you have a big interface, you have a lot to learn, and if there's not much functionality, you're not getting much benefit from it. So a shallow class just doesn't provide much leverage against complexity. Instead, what we want is a deep class, something with a really simple interface and yet tons of functionality behind that interface. This is great. This gives us leverage against complexity. So as an example, here's a typical shallow, by the way, classes can be shallow or deep, but also methods can be shallow or deep. Larger things like modules or subsystems can also be shallow or deep. So this slide shows a not unusual shallow method. I see methods like this all the time, particularly when you look at student code. But actually, I see this in industrial code also. This method, its interface basically includes the entire implementation. You have to know everything about what this method does in order to know how to invoke it. And in fact, if you invoke this method, you actually have to type more keystrokes to invoke the method than if you just did what was inside the method. If you threw away the method and just typed the body of the method instead. So there's essentially no benefit from this class. In fact, it's just adding complexity. It's forcing people to learn more, to learn an interface, and you get back nothing for it. So this is sort of the worst case sort of shallow method. I see a question in the chat. I picture the width of the class means that it also must be relatively small. Well, if you define width as sort of the X dimension, if it's deep, a class can still be very, in my analogy, if I go back to that slide, this deep class does not appear very wide, but it's very, very deep. And so in fact, it has a lot of functionality. So it might have a lot of code inside the class. Okay, so shallow method. So what's going on here? Well, the problem goes back to how we teach computer science. The common wisdom that people are taught is that classes and methods should be small, not deep, but small. For example, how many of you have at some point in your career heard somebody say, any method larger than n lines long, you should find a way to chop it up into multiple methods? And for those of you that heard that, can you just chat, what numbers of n have you heard? What's the smallest number of n you've heard? Any methods larger than n lines should be chopped. Any method larger than 30 lines, 20 lines, any method larger than 5 lines, any method larger than 3 lines should be chopped up. Yeah, I think probably most people probably have heard in the 10 to 30 range. You've probably heard that. By the way, this approach is advocated by Robert Martin in his book Clean Code, which there are parts of that book I agree with. This part I very strongly disagree with. And Robert Martin, or Uncle Bob as he's known, says something like that. The most important thing is to make methods small, and once you've made them small, the next most important thing to do is to make them even smaller. And he says ideally a method should have at most one control statement, one if or while statement in it. And the body of that should have at most one statement in it. If it needs more than one statement, you should chop it up and make a separate method for that. Well, this approach results in an incredibly high level of complexity that I call classitis. Classitis is what happens when somebody says classes are good and somebody else thought what they heard was more classes are better. In the classitis world, you try and make everything as small as you possibly can. That each class does exactly one teeny tiny thing, and if you need anything more, put it in a separate class. So every new feature results in a separate class. The problem with that is you end up with an enormous number of classes with an enormous amount of interface, almost no complexity hiding. And so it results in a high level of complexity in systems. Turns out that classitis is unfortunately fairly rampant in the Java world. It's not that the Java language itself requires this approach, but just the philosophy that's come about in building the library is one of lots of teeny tiny classes. One of my pet peeve examples is for many years, if you wanted to open a file in Java and read serialized objects from it, you had to create 3 objects to do that. First, you open a file stream that allows you to read and write the file, but a file stream does not provide buffering. If you want buffered I/O, you have to open a second object on top of that, a buffered input stream on top of the file input stream. Now, the Java designers probably thought, well, not everybody wants buffering, so we shouldn't just build that in. People that need it should ask for it, and people that don't need it shouldn't ask for it. And it sort of sounds plausible, but the thing is, essentially everybody wants buffering. When was the last time any of us opened a file where we didn't want input to be buffered? Okay, I've probably done it at some point in my career, but I can't remember the last time I did it. And so one of the things about class design is you want to make the common things really easy. So anyhow, in Java, you have to create 2 classes. And by the way, if you forget to create that buffered input stream, everything will work. It's just your program will be crushingly slow as it reads individual characters one kernel call at a time. But if you want to read a serialized object from the stream, then you have to create a third object to do that. Now, in recent years, they've added a new constructor that I believe will create the combination of file input stream and buffered input stream in a single call. They recognize this problem. But this is an example of, again, too tiny classes adds complexity. So I would argue length is important. It is, but it's not the most important issue. Abstraction is the most important issue. We want to provide simple ways of thinking about complicated things. We want to have nice deep classes. And then, so I would argue first, make your classes really deep. Now, so lots of functionality, tiny interface. Now, if it turns out that the implementation is getting too complicated, then see if you can find ways of dividing the implementation up. But the most important thing is to get that deep interface for your users. That's much more important. It's more important to have a simple interface than it is to have a simple implementation because many more people are affected by the interface. Let me just skim the chat window here for questions. Let's see. Okay, I don't see any specific questions there, so I'm going to go on. So what's an example of a deep interface? My favorite interface in the entire world is the file I/O interface from the original version of Unix, developed in 1970 or 71, that still exists today in Linux. This interface consists of 5 functions, and they all have really simple interfaces. The only complication in the interface is the flags argument to open. It has a little bit of complexity associated with all the different flag values that can be, but it's really simple interface. This interface covers hundreds of thousands of lines of code in the kernel. It's an enormous amount of code to implement all of this. And that code does stuff like managing how files are represented on disk and allocating disk blocks and implementing directories and path lookup and managing permissions and security and scheduling disk IOs and a block cache, device independence. There's an enormous amount of complexity that is hidden below that interface. And users just get this wonderful, amazing, simple interface. It's a really cool interface. I see a question, is readability a criteria for good code? Absolutely. I mean, readability and complexity kind of go hand in hand. If code is really simple, it's really easy to read. If it's really complicated, it's hard to read. Yes. I'll come back and talk a little bit more about that in a minute. Any questions about deep classes and why this is important? Or if you disagree, and by the way, I'm delighted to hear, reason to disagreement as well. Okay, let's go on to my second concept I want to talk about. General purpose classes are deeper. Actually, I see a question in the chat window. Do you think there should be a limit for method depth? No, no, I can't imagine a method being too deep. Say, oh, the interface is too simple, or oh, you have too much functionality. Boy, I can't imagine that. The implementation might become too complicated, and so you might start looking for ways to split it up. But I've never seen anything that I thought was too deep. Okay, so the next issue is general purpose classes. This cuts to what I think is a really important problem that everybody faces when you're doing software design. Excuse me. When I'm designing a new class, I can take two approaches to that. One way is I can build something that's specialized, that meets my needs today, and then come along later on and generalize it if need be. Or I can try and build a general purpose class. And I faced this problem myself for years and struggled trying to figure out what's the best approach. Should I make things general purpose or should I make them special purpose for today's needs? And my initial thinking on this was that you should start off specialized. Since we don't know how the class is going to evolve, just build what you need today. And then if it turns out it's going to be reused, you want something general purpose, you can come back later and refactor it. Refactoring is an essential part of software design anyhow. And so when I first started teaching the software design class, this is what I told students, because this was my best guess. After reading students' projects for a couple of years, I realized I was wrong on this, really wrong on this. What happens if you try and build things that are specialized is you actually end up with APIs that are really complicated. And you end up with information leakage where there's dependencies between various classes and modules in the system where they share information. In contrast, if you build things general purpose, they end up simpler and deeper. And let me give you an example to illustrate this. At one point in the course, the first project was students had to build a simple GUI text editor. It displays a file on the screen, you can click to select and insert text. And the students had to build a class to store the text, represent the text in memory for the editor. And this was back when I was suggesting the specialized approach. So most students took a very specialized approach where they would design the API of the text class to correspond to the various user interface actions, like inserting a character or typing the backspace key or typing the delete key or deleting the selection. Again, specialized for the needs of its client, which was the user interface. Problem with this is it ends up with really complicated APIs, a lot of methods, a lot of information leakage with user interface. For example, there's things like cursor and selection, which are really user interface things, are now understood and embedded in this low-level text storage mechanism. Or the idea there's a backspace operation, which is distinct from a delete operation. Backspace deletes in one direction and deletes in the other direction, deletes in the other direction. So there's all this information leakage. And now every time you add a new operation in the user interface, you end up adding a new API in the text storage mechanism as well. So tremendous complexity. But a few students took the general purpose approach. The general purpose approach is basically two methods for text. Insert, it's a string of text at a position, and delete, a range of text. So you end up with much fewer methods. The methods have really simple APIs, and you end up with much better modular decomposition. So instead of having notions like cursor and selection, there's this general purpose thing called a position in the text file. And the cursor is probably in the user interface is represented with one position, and the selection is probably represented with two positions. But we have now this very clear decomposition between what's in the text object and what's in the user interface object. So it's become clear to me the more I teach the class that the general purpose approach is absolutely the right way to go, virtually always the right way to go. And so what I advise people now is you should design your classes from the beginning to be, I call it somewhat general purpose. So don't get carried away. You can go way overboard on this. But the idea is when it comes to the functionality of the class, focus on what you need today. Build the functions that you need today. So what it does. But when it comes to the APIs, what the interfaces look like, design the interfaces to be general purpose. So they're not specialized for how you're going to use things today. Again, if you go back to the text thing, the interfaces to the text object are very general purpose, not at all specialized to any particular user interface action or how the user interface is going to use the class. And my experience is that even if you never actually use the class for more than one thing, it's only used for one purpose, you'll still find that it's simpler and easier to maintain. This is just an uncanny discovery to me. Again, I'd programmed for more than 30 years before I figured this out and was actually teaching the class and seeing students do things in different ways that suddenly made this very clear to me. And this is part of a much more general element of good software design, which is avoid specialization. So when we think about software design, our overall goals, we're trying to manage and reduce complexity. Making classes deep doesn't necessarily eliminate complexity, but it hides it down inside classes where most people don't see it. If you can avoid specialization, that actually eliminates complexity. It completely takes it off the board. It just simply does not exist. So it's the best possible way to deal with complexity. And this happens at many levels. So general purpose classes are one way of avoiding specialization. Or in code, trying to avoid special cases. I find one hallmark of poor code is that it's riddled with special case after special case after special case, where in fact there is a simple general purpose way you could have done things that handles all the special cases without special code. That code is simpler. Or reducing the number of places where you have to deal with exceptions, because exceptions suddenly result in specialization, or so things aren't working the way you want. They're a source of complexity. So this general idea of trying to avoid specialization as much as possible is really fundamental to software design. Questions about this? Let me just take a quick here, look at the chat window. I see a comment, the and in your description is suspect. I'm not sure I know which and that's referring to. Duke, do you want to just
I think that was referring to the previous comment about the really long method of 50,000 lines.
Oh, the really long method. Oh, okay. All right, any other questions about this? Okay, so now I want to talk a little bit about mindset. To me, one of the most important ways to get good software design, well, an essential way, is you have to have the right mindset. And there's two ways of thinking about software design, which I call tactical and strategic. In the tactical approach to programming, your most important goal is to get the next thing working, get that bug fixed, get that next feature fixed. It's kind of hard to argue that this was a bad idea. Surely that's the whole goal of programming, is to build functionality that works. How can that be wrong? Well, the risk of this approach is that when you take this mindset, you tell yourself, I'm going to write code that's generally pretty clean and readable, but if I have to take a little tiny shortcut or a kludge, little tiny thing, it's not a big thing, I mostly care about design, but a little thing, that's okay to get the next feature working. The problem is this snowballs. that you very quickly discover you've got not one or two or 10, but hundreds and thousands of these kludges because everything you do adds a little bit of complexity. And so you end up with a system with a bad design and very, very high complexity. And I think you have to realize, really important to realize that complexity is incremental. That is, system doesn't become complicated because you made one fundamental mistake and that just blew your complexity out of the water. Complexity comes about because of hundreds or thousands of little tiny things, none of which seems like that big of a deal at the time. But it's the accumulation of all of these things that makes a system complicated. And the problem with that is that if a system becomes complicated this way, it's extremely difficult to fix it because there's no one thing you can fix in order to fix the problem. You have to fix hundreds or thousands of things. And typically that task feels so overwhelming that most people just say, I don't have time for that. And they go on to the next thing where they add the next little kludge in. There's an extreme of this mindset, which I call tactical tornadoes. As far as I can tell, every engineering organization has at least one of this kind of person. These are people that are amazingly fast at getting that bug fixed or the next feature fixed. Like bosses often view them as heroes that, boy, when push comes to shove, give the job to this person and they will get it done before you know what's happened. Well, but typically what happens is, in fact, they only get it 80 or 90% done and they leave a wake of destruction behind them in terms of kludges and problems that other people have to come along and fix up later. And it's sort of sad that these programs are, as I said, sometimes viewed as people sometimes viewed as heroes because I think they're extremely destructive. But I'll bet everybody here knows somebody like that. Who knows? If there's 100 people out there listening, it's a good chance at least one of you is one of these, and you should be maybe asking yourself some questions about that. So, to me, the bottom line is that yeah, working code is important, but it's not enough. That's not enough by itself. Instead, I argue for a strategic approach to programming. And the strategic approach, of course, we're going to make code that works. But the most important overall goal is to create a great design. That's the most important goal because that's what will allow us to develop quickly in the future. And at any given time, if you look at a project, the odds are most of the development of that project is still coming in the future. Most things, there's still huge amounts of development coming. And so it's important not just to get the job done today, but to make sure we can work quickly in the future as well. And so that means you have to minimize complexity. That means you have to sweat the small stuff, not let those little things creep in. The overall idea is that we'll take a little bit of extra time today, but it will pay back in the long run. And so for that, I have a graph on the right side of the slide. So this is a totally fake graph in that I have no data for this, unfortunately. I know of no, in fact, I know of no way to even gather this data, but this is my personal belief about what happens. So if you take the tactical approach, the red line, you develop faster at the beginning, but the problem is as cruft accumulates, you develop more and more and more slowly over time. Whereas if you take the strategic approach, you'll develop a little bit more slowly initially, but, and by the way, over time, complexity will still accumulate. Even the blue curve is still turning over. Fundamentally, I think you can't win the battle against complexity. You can only slow it down. You can't completely prevent it from accumulating. But what happens is that over time, the blue curve actually allows you to develop faster than the red curve. And at some point, you reach a crossover point where it turns out you would have gotten the job done faster if you just took the strategic approach from the beginning. So the interesting question in this graph is, where is the crossover point? How long does it take before my good design pays off? If it's going to take 20 years, then it's probably not worth it. Again, unfortunately, I don't know of any measurements to answer this question. I've asked people, when I ask people, most people tend to think it's somewhere between 6 months and 2 years. And that's where I would say also. And the reason I think it's in that time period is because by the time your code is 6 months old, you've forgotten how you wrote that code. And so anything that's non-obvious about it, fundamentally, you're going to have to face that when you make any changes. And so you can't just remember all of the details involved. So that's my opinion. Unfortunately, again, I don't have data for this. I would love to see somebody get data, but I don't really even know how you'd measure that data. By the way, of course, technical debt is just another way of talking about all this. The tactical curve is basically creating technical debt, and by technical debt, it's borrowing time from the future. You get time back, time today, and you'll pay time in the future. And by the way, you will pay that time back with interest. Let me take a quick look at the chat window here. How does Agile align with tactical versus strategic programming? Oh, that's a really interesting question. So I think Agile can be totally consistent with strategic programming, but it can also be totally consistent with tactical programming. Sometimes people take Agile to the extreme of thinking we should never actually do any design, but basically just debug the system into existence one piece at a time. So Agile is neither tactical nor strategic. I'd encourage you, if you're using Agile, which I generally like, I would say do it in a way that's strategic. So now the next question is, how much should we invest? Or how much can we afford to invest? And you see a range in different companies. If you look at most startups today, 100% tactical. They feel like they're under tremendous pressure to get those first products out really quickly. You convince yourself, we can't afford to spend a lot of time now. We've got to get products out so we can get our next round of funding. Yeah, this is going to cause problems later on, but we'll be able to clean it up later. After our IPO, we'll have so much money, we can hire legions of programmers to come in and clean up all the mess we're making right now. And if you take this approach, the code base becomes spaghetti really, really fast. And in practice, I'm not convinced you can ever actually go back and repair the damage. If you can, if you do it at all, it's really expensive. Uh, I think most times the damage is just permanent. Now, you can succeed in a company with this approach, and startups do it all the time. Honestly, Facebook was a poster child for this approach. In the early days, the mantra of the company was move quickly and break things. And in fact, they did both of those. You know, uh, Developers were told you were expected to commit code into production your first week on the job. And this is very empowering for developers. These are heady stuff for a fresh college grad who think, I'm making the Facebook site better in 7 days, 5 days on the job. But the problem with this is that it led to just a code base that was a train wreck. The Facebook code base was notoriously hard to understand, really unstable. At one point, I had a couple of graduate students who went and spent a summer internship at Facebook working. And they'd been complaining about my demand that they do good design and write comments in their code. And they came back from summer ashen-faced, thanking me for the culture I had in my group at Stanford. They basically said that every Monday, a new push of all the infrastructure comes out to everybody, and everything breaks until Thursday. It takes till Thursday to get everything working again. Then you have one day to actually make progress before everything breaks again the next Monday. So anyhow, Facebook eventually realized this, and they changed their mantra to move quickly with solid infrastructure, implying that we actually do want to spend time, invest in some of our stuff to make it easier for people to develop. So you can succeed. Obviously, Facebook has been fabulously successful as a company, but I would also argue you can succeed with a strong design culture too. You don't have to be tactical to succeed as a startup. It's not clear to me that being tactical even helps you as a startup. It's easy to convince yourself that you need to be tactical in a startup, but I'm not convinced that it really helps. So for many years, between 2000 and 2010, there were two companies in Silicon Valley known as having really strong design cultures, and they were Google and VMware. And these companies attracted all the best engineers. Google and VMware both said, we basically never lose engineers except to the other of these two companies. And of course, both of those companies have also been phenomenally successful. So you don't have to be tactical in order to succeed. And an interesting thing is, if you had to ask yourself, what's the most important, easiest way to develop software, high quality software quickly? What's the best way to do that? The answer is hire good engineers. That's the best way. If you want to be able to develop good software quickly, you want the best possible engineers. Well, do good engineers want to go work on a spaghetti code base? Probably not. They want to work in a place with a strong design culture. So I would argue it's in your own enlightened self-interest to create a strong design culture because it will get you the best engineers, which allow you to develop most quickly. But again, so but how much should you invest? And what's the right amount to invest? And I don't have a perfect answer to this question, but what I would say is don't feel like you have to do heroic things. For example, you can't design your entire system up front. You can't visualize the impact of your design decision. You have to take things in small steps. So I would say make lots of small investments, not huge investments, but small investments. And I would argue, suppose these add 10 to 20% to your schedules today. I would argue most organizations can probably accommodate a 10 to 20% slow down in my current deliverables if that's going to allow me to develop faster over the longer term. And I believe with an investment on that level, you can create a pretty good design that will pretty soon allow you to develop way more than 10 to 20% faster. You might ask yourself, how slow does development get in a really bad code base? And I'd argue it slows down a lot more than 10 to 20% over a good code base. So what does this mean? It means, well, when you're writing code, spend some time on design. Recognize the limits of this. You're not going to be able to get everything right up front. More important to leave time for iteration and refactoring. Write some good documentation, right? Definitely document your code as you go. And then over time, be continually revising and improving because you won't be able to get things right at first. You recognize you can't get that right. So plan on needing to go back and revise and leave time for that. And furthermore, I think there's an important philosophy to keep in mind when you're changing existing code. I think a lot of times when people go back into code to fix a bug or add a new feature, they have the mindset of, I want to do this with the fewest possible lines of code changed. Typically, they say this out of fear because they're afraid that if we change a lot of code, they're going to break something. But the problem with this approach is that it's going to add cruft because the fewest lines of code is probably going to introduce bad stuff. I would argue instead, when you go to make a change, ideally, after the change is done, the system should look the way it would have been if it had been designed from the start, knowing everything you know now. That's ideally. But what would the design have been like? Now that I know what I know now, what would the design be like? That's how the system should look after a change. Now, this isn't always practical. I know, there are times when getting it this right would require massive revisions and your schedule doesn't have time for that. So I get that. But that should be the goal you keep in mind, to try and get as close as you can to that. And in general, I believe when you go to make changes, you always must find something to improve because the odds are, in spite of your best attempts, you're probably making at least something a little bit worse, probably. And so you have to compensate for that. Sort of like, always you need to clean up somebody else's litter because you're probably accidentally dropping some litter yourself. So what I would say is ask yourself, is this the most I can afford to invest right now? Ask yourself, look in the mirror and ask yourself that question. And then go ask your boss. Say, boss, is this the most, really, truly, this really the absolute most we can afford to invest right now? And then have your boss ask their VP the same question. And just do the most you can. And if you ask yourself that question, I think you'll find you can probably invest a little bit more than you're currently investing. And if you have to do things like, I know everybody reaches schedule crunches, and at the end of a schedule, kludgy things happen. Okay, that may be inevitable. Try and get your boss to allocate time after that schedule completes to go back and clean things up. Or to have a few people in the project whose mission is to do cleanups while the rest of the people are going off and building new features. But just find some way to continually make small investments. I believe that's the way to do this. You don't have to be heroic, just lots of small things. So coming back to the course, does the course work? Well, it's a little bit hard to know. And of course, you can't make somebody a great software developer in 10 weeks. That's not possible. I think it's the beginning of a process. To become a great developer, I think takes probably 5 to 10 years of conscious work and getting good feedback and thinking about your code and so on. So I really need to come back and ask the students in 5 to 10 years. And actually, it's getting to be close to 10 years since the first time I taught the class. So I'm actually thinking about having a reunion of all the students who took the class over the last 10 years to bring them back together again and ask them to talk about whether it helped, what they learned in industry, what parts of the class worked, which parts didn't work. So I don't really know for sure whether the class is working, but I can tell the energy in the class is really a positive energy. Students have a great time in the class, and I can see the tone of the conversations in class changing over the course of the quarter. In the first design review, students are really hesitant. They're not confident in their ability to criticize other people's designs. They don't want to criticize their friends. They tend to be very tentative. And then they get their code reviews from me, which are not the slightest bit tentative. And by the end of the course, the tone of the discussion changes completely, where students are having really interesting discussions, arguing about what things this particular approach make a system simpler or more complicated. And I can tell students are thinking about their code in very different ways than they did at the beginning of the quarter. So that's great to see. I can also say that even if the students aren't learning a lot in the class, I think they are, I actually have learned a surprising amount by teaching the class. Like actually enjoy reading the assignments, even though it's a ton of work. And by the end of the quarter, I do need a break. After doing this sort of 3 design reviews over the quarter, that's about all I can handle for a period of a year or so. But it's been really interesting for me because I get to see the same project done 9 different ways. Everybody's doing the same project. And so you can compare different approaches. And it's really interesting to see, you can read a piece of code and you can just tell it's complicated. It feels complicated. But then the question is, why is it complicated? And what could you do instead to make it simpler? And so that's been a really interesting process for me. As I mentioned earlier, the process of teaching the course has actually changed my view about software design in a few ways. So that's been fun. So I think the course is working, but it's still a little early to tell. So after I'd been teaching the course a couple of years, I gave a talk or two on the course, and people said, John, you should write a book on this. And so about 5 years ago, I had a sabbatical, and in fact, I did. I took my sabbatical to take the ideas from the class and write this software design book, A Philosophy of Software Design, which Mark mentioned at the beginning of the talk. And the goal of this is to see if we can get the ideas out to more people, and also I'm hoping to stimulate more discussion about software design in the broader software community. I'd love to have people debate, are the ideas in the book good? Are they bad? I'm very interested in hearing actually if people disagree with any of the ideas in the book. And also, one of the things I've tried to do in the book is to define terminology with things like deep classes, for example, that give people terminology that we can use to talk about the principles or strategic versus tactical design. That hopefully, again, hopefully that will stimulate more discussion and awareness of software design. And like the class, the book is more philosophical than prescriptive, so probably works best in conjunction with code reviews. I'm curious to hear from people if you just read the book in the abstract, does any of this make sense, or do you need code reviews in order to make the ideas concrete? So just to conclude, and then I'm happy to take questions, I absolutely believe you can teach software design. I totally believe that. The current approach, unfortunately, is not very scalable. I can only teach 18 people a year, so that's a little bit discouraging. I think that a set of principles are actually emerging from all of this, and uh, my long-term goal still is, again, I'd like to try and get a greater sense of design awareness in the software community, either through the book. I'm really interested in hearing criticisms of the book, things you don't agree with and why, or new ideas or better examples. I created a mailing list for people interested in talking about stuff like this. It's listed on the slide. It's a relatively low traffic list. I don't know, maybe half a dozen messages a month or so. But I think a really interesting question in all this is, as a community, can we agree on a set of software design principles? Is there one set of principles, the right way to do software design? And when I started on all this, I wasn't sure. It seemed possible to me that there might be 2 really great software designers who took totally different approaches, and yet they both produced great software. Well, after the book's been out there a while in the class, I'm actually not hearing a competing view of software design principles. So I'm starting to think cautiously that, in fact, maybe there really is one absolute set of principles. But this is still early days, and again, I'm really interested in any ideas any of you have on software design or what those principles should be. So with that, let me stop. I realize my hour is just about up. Happy, if people need to break off of the call, I understand completely, but I'm happy to stay around and answer questions. And I'll stay around as long as you have questions you want to ask. So feel free to, you can either ask in the chat window or just unmute yourself and ask questions. So let me make this sharing go away.
So Duke, do you want to speak up?
Yeah, can you hear me?
Yep.
Really two things. One's really quick. I was interested in, so you have a project that the students do. And one of the ideas, like I was trying to come up with a curriculum and, or like just to kind of imagine one that would have been helpful to me. And it would have been to have a project and all the requirements going into it. And it builds upon itself and such. And then at a certain point, the requirements change. Like, oh, you know what? We don't want that anymore. And the reason I suggest that, or I was thinking about it that way, is it really rewards design to be able to make those changes more easily. If I mean, maybe the first time you do it, it's a surprise, like. Anyway, that's just something I was thinking about. What I really wanted to ask was way back in the beginning, you were talking about the three best programmers that you knew, and you sat down with them and asked them what made them so good, and they couldn't answer that, right? And to me, that kind of implies that it implies talent. Um, so I've been in this business for a long time, like 20 plus years, and I'm not a great programmer, and I understand that. I work really hard to be good, but I've met talented people. Few, less than five in the many places I've worked in the years I've worked. Um, I don't know. I guess that's just more of a comment than a question. So.
Okay, thanks. Well, let me go back to your first comment about having students work in an environment where the requirements change. I think that would be a really interesting challenge in the class. When I started teaching the class, I did a slightly different twist. I had the students work on their own projects, and then for the third project, I exchanged projects, made students take a different group's project and add new features to it. And then along the way, they were invited to also clean up problems they saw in the project. And I think that was a useful exercise, but I eventually decided not to do that. The students didn't like it very well because they felt like they spent all of their time trying to understand somebody else's projects and clean up stuff in that project versus actually making progress on their own. And so I eventually decided that from a standpoint of teaching design, it would be more useful to students to have a new clean slate design to do on their own than to try making extensions of somebody else's project. But of course, extending somebody else's work is a much better exercise for what you're going to experience in the real world. Similarly, having requirements change underneath is also a great experiment for the real world, but might have been frustrating for students. But it's an interesting thought. I see a chat question. Do you think instructors adapting different learning styles when teaching coding and the methodology to accommodate these learning styles is important? How do you think they would factor in as educational sector aware of the necessity if there is one? So I think the question here is about, you're talking about learning style, that maybe some students learn better in one style and other students in a different style, as opposed to the conceptual material being different in the class. I definitely recognize the fact that some styles work better for some students than others. And so having different instructors use different styles sounds great to me. So that over the course of their career, every student is likely to get a style that works well for them, for example. So I think that makes sense, yes. I see a question. How much of a role do visual models like UML flowcharts and mind maps play in writing good code? Well, this may reflect my prejudice, but I'm not a fan of any of those. Actually, I grew up programming in the days when flowcharts were used all the time, and Fortran was my first programming language. The problem with flowcharts, I haven't used UML, so I have only uneducated biases about it, no educated biases. The problem with flowcharts is that you focus on the details rather than the abstractions. The flowcharts are all about very, very low level details. I don't personally, I think flowcharts, if anything, get in the way of good design. I'm skeptical of UML for the same reason, but I don't have enough experience with it to really give an educated opinion. Question from Adina, what programming language do you use in your course, or it's free to choose? No, I want everybody programming in the same language. First of all, it needs to be a language I know. And second of all, it's easier for students to code review each other's projects. We used Java in the early days, and now we use C++. That's because that's what Stanford students tend to be most familiar with by the time they get to this class, which is late in their undergraduate careers. Other questions?
So I had a question about the idea of do design up front, but it sounds like you're also recognizing that there's stuff you're not going to know till later on that you'll want to change for. So is that 10-20% that you're saying is kind of what feels like the sweet spot, doing design up front and also making the changes that you need to evolve your code as you become more aware of those things, or is that something separate?
Yeah, I think what I was thinking is 10 to 20% is the amount of extra time you spend over a fairly purely tactical approach.
Okay.
That is,
Very cool.
you don't need to go 3 times as slow in order to have good design. And if you're willing to spend 10 to 20% extra time, you can do pretty well.
Okay. Cool. Anyone else have any other questions? Cool. Well, John, thank you so much for coming. This was great for me, and I highly recommend the book. I put a link to it, but it's very, very useful. It was very eye-opening for me, like I said. So I highly recommend that. It's all marked up now because I had a pen when I was doing it, wrote down all kinds of things. But highly recommend getting a copy of the book. I will post this on the YouTube channel too here in a little bit. So if you got anybody like, hey, we want to watch through a piece of that and kind of discuss it as a team, it'll be up there. John, thank you so much for coming.
Thank you, and thanks for inviting me. And again, I'm always interested in receiving feedback. And in fact, one of my favorite sayings is compliments make me happy, but criticism makes me better. So I'm actually very interested in receiving disagreeing feedback. If you think anything in the talk was incorrect or misleading, or the ideas in the book are not good ideas, really interested in hearing about that. Again, this is all in a very fluid, changing world. So anyhow, thanks for your attention, and go out there and design strategically.
Thank you. Everybody have a great day.